Each of these bonds in the water molecule are polar. The oxygen has a higher electronegativity than the hydrogen, and therefore this is a polar bond. So we can assign a dipole moment to each of these bonds, and we can write a dipole arrow and show the direction and the magnitude of that dipole moment. So the length of the arrow is going to tell me the magnitude, how strong is that dipole. And the arrow, the direction, shows me which direction the electrons are being pulled. So these two dipole arrows are of the same length because they're both dipoles for oxygen and hydrogen. So they're the same kind of bond. So the length of that dipole, the strength of that dipole is the same for both bonds. However, we can see that they're in different directions because of the shape of the water molecule. Remember that water has a steric number of 4, and so an electron arrangement that's tetrahedral, but 2 of those are lone pairs, and so the molecule itself is bent. And that means that these dipoles are going to be 120 degrees from each other. If we look at the heat map for where the electrons are in this whole molecule, we can see that there's more electron density up here where the oxygen is and less electron density down here where the hydrogens are. So this entire molecule has a dipole moment as well. The dipole moment for the molecule is the addition, the vector addition of the dipole moments for the bonds. So how do I add dipoles? So if you have drawn the dipoles for each of the bonds, then if you take one of those dipole moments and move its tail over to the head of the other dipole moment, and then you draw a dipole from the tail to the head of the other one, you will get the addition of those two dipole moments. And so you can see that if we add these two bond dipoles, we get a dipole moment that goes positive from the hydrogens up to negative to the oxygens. And so it is a dipole moment that is directly in between, bisects this bond angle, and has positive at the hydrogen end and negative at the oxygen end. So I can just move this molecular dipole over here, and I can see that that is the dipole moment for the molecule. When a molecule has an overall dipole moment, a molecular dipole, then we say that the molecule is polar. Let's look at another example. Let's look at the molecule CO2. So the very first thing I need to do is draw a Lewis structure so I can figure out how the atoms are bonded to each other. So the Lewis structure for CO2 looks like this, and I can see that I have a carbon-oxygen bond here and a carbon-oxygen bond here. This carbon is sp hybridized because it has a steric number of 2, and so it's linear. And it's important that I understand the shape of this molecule as well as its Lewis structure. So this is linear, steric number of 2 atoms. So I know that it's linear, and so my dipole moments are, for each of the bonds, are going to be 180 degrees from each other because the bonds are in a linear arrangement. So if I look at the colors for carbon and oxygen, I can see that they're different. And so I would expect there to be a dipole moment for each of these carbon-oxygen bonds. And so if I draw those dipole moments in, the oxygen's more electronegative than the carbon, and so I'm going to have dipole moments that look like this. And if I put those head to tail and I look at the addition of those two vectors, you can see that those two vectors are pulling in exactly opposite directions. So if I move one of these over, they're going to be exactly on top of each other, and the positive will cancel with the negative, and my net result is that I have no molecular dipole because these two bond dipoles cancel. So in spite of the fact that CO2 has bond dipoles, the molecule is non-polar because the bond dipoles are going to cancel. So it's a non-polar molecule. Let's look at one more, a little bit more complicated problem where we have a molecule that has a three-dimensional shape like a tetrahedron. It's a little bit harder to see in 2 dimensions when we draw it on a paper. So for instance, if we have C carbon, Cl2, H2, then we have the following Lewis structure, and I'm going to draw the 3D shape of it. So if I have a chlorine here and a chlorine here, then this hydrogen has to come out at me, and this hydrogen has to go away from me. And so if I think about the dipole moments for these bonds, I have to draw those dipole moments in the shape of the molecule, right? So if I think about which of these bonds actually has dipole moments, the carbon and the chlorine are different colors. And so carbon and chlorine have dipole moments. And the chlorine is more negative than the carbon. And so I am going to have a dipole moment in this direction and a dipole moment in this direction. Now, if I look at the carbon and the hydrogen, hydrogen's a little less yellow than carbon, but we don't consider that enough of a difference in electronegativity to call this bond a polar bond. And so carbon and hydrogen are typically always thought of as non-polar bonds. So I don't have to draw a dipole moment for the carbon and the hydrogen, and because I judiciously drew my tetrahedron such that the chlorines are in the plane of the paper, now I have an easier time actually seeing where this molecular dipole is. So I'm going to take and move one of my dipole moments tail over to the head of the other one, and then I am going to draw my molecular dipole moment, tail to head. And so my molecular dipole is one that bisects the chlorine carbon chlorine bond angle. So it bisects this bond angle, and these chlorines are more negative than this carbon hydrogen end of the molecule. So the overall molecular dipole points between the two chlorines.